So this is going to be a video for the data processing for the first lab for the Venturi meter. So I'm going to use MATLAB for this video. You can use Excel if you want, it doesn't matter. But what I've done here, I've started off by clearing out my memory, so that's going to clear the workspace over here and the command window down here. Next, I have some constants that we're going to use for this report. I have gravity, the water viscosity and density, and the throat diameter. So for the water viscosity and the density, you would have found that by measuring the water temperature during the lab, and then you can look this up later. For the throat diameter, you're going to have to look at the lab manual. For station number 1, it's this diameter, and for station number 2, it's this diameter, and those are both in inches. So the number for the station was at the top of the Venturi meter, so if you have pictures of the station when you took the lab, then reference that. Next thing I've done, I've converted to SI units, so I've made some factors here from inches to centimeters, and inches to meters, and pounds to newtons. I don't care what kind of unit you use. You can use SI if you want, or English units. You just have to be consistent throughout the report. Okay, so what I've done just right now is I've imported my data into MATLAB. So you're going to have your data stored somewhere. In my case, I have it in an Excel file right here. I have 2 sheets open. One of them is for my pressure data, so I have the piezometer heights for each of the taps for each of the runs. So, this is tap 1, then tap 2, tap 3, etc. And then I have each of the runs, as I said. The other sheet is for the flow rate, so I have all 6 runs again, and then I have the time that we had for each time that we added 15 pounds to the counterweight. Let's go back to MATLAB. So to import it, what I've used is file name equals, and then my file name. So in my case, I've saved all of this data in a file called exp1_data. Okay, so that's going to call that file into MATLAB. Now I want to sort my data into the pressure data, into the flow rate data. So that's table 3 and table 4. So I've done that by H range, meaning all of my pressure data. In this case, the H is corresponding to the height. So H range equals A3 to H13. So let's go back to Excel. I want all of this data right here. That's going from A3 to H13. So I don't care about having, this text up here. I just want all of this data. Same thing for the flow rate. I have T range, meaning kind of the time. T range equals A3 to G8. So A3 to G8. All of this data. Let's go back to MATLAB. And now I'm going to basically import this data, now this pressure data that I have, by assigning it to kind of a matrix here. So I have matrix A. It's going to read this file H range, and it's going to assign this variable A. And then same thing with my flow rate data. Okay. So now at this point, I'm going to sort this data. So now if I look here, I have A right here. So I've fully imported this into MATLAB as a variable right here. So here's all of our data that we just had for the pressure. And then same thing, B, that's all of our data for the flow rate. Let's go back here. Now I'm going to sort the data into a separate array for the diameter, the axial position, the pressure head, the water weight, and the time. So let's go ahead and do that. So we're going to have D equals A, all of the rows in the first column. So let's look at this now. So I want the diameter here, so we want it in this matrix A. So let's look at this. And then I have a colon here, that means all of the rows in matrix A. And then I want the first column. So that's this column here. We'll go back to Excel really quick. So this is matrix A is basically highlighted right now. That's what's in MATLAB. I have all of the rows in this first column. That's for our diameter. And right now it's in inches, so we're going to convert that later to meters. Okay, for the axial position, I'm going to do matrix A, all of the rows in the second column. So all of the rows in this second column. Now we're going to import all of the height data. So now we're going to do matrix A. I'm going to do all of the rows once again. But this time, I'm going to do columns 3 to 8. Okay, so let's go back to Excel. We're in matrix A. And I'm saying all of the rows for columns 3 to 8. So all of this is all of the height data. Go back to MATLAB. Now we're going to get our weight. Okay, so the weight is going to be in matrix B, all of the rows, and the first column. We'll do the time, matrix B, all of the rows for columns 2 to 7 this time. Okay, now let's go back. Okay, just making sure I did that right. Okay, so go to this table. We had the weight, all of the rows in the first column. Then we wanted all of the time data. So all of the rows, and then from columns 2 to 7. 2, 3, 4, 5, 6, 7. Okay, so there we go. Alright, now I'm just going to convert to SI units, so I'll do that and I'll come back. Okay, so now I've converted all of this stuff right here into SI units. So obviously time's the same, that's just going to be seconds, but all of this stuff I've converted using the factors that I've made up here. So diameter, I'm converting that to meters, the axial position to centimeters, the pressure head to centimeters of water, and then the weight, I'm going to convert that into newtons. Alright, the next thing we're going to do is we're going to initialize some arrays. So I'm going to do that for the actual pressure head, the theoretical pressure head, the actual flow rate, the theoretical flow rate, the discharge coefficient, Reynolds number, and then the head loss. So I'm going to initialize these arrays using the zeros function. Basically, I'm going to do that so we can save some of the memory that we have and some of the time later on once we build these up in MATLAB. So I'll be back. Okay, the next thing I've done here is I've initialized my arrays. So we have the actual pressure head, the theoretical pressure head, the actual volumetric flow rate, the theoretical volumetric flow rate, the discharge coefficient, the Reynolds number, and head loss. So again, I'm using the zeros function. So once I do this, I'm basically gonna, in this case, make a matrix with 11 rows and 6 columns, and they're all going to be 0. So I'll go through this briefly. The actual head, we had 11 taps and we did 6 runs. The theoretical head, we want to do the same thing, so we want 11 readings and for 6 runs. The actual flow rate, so for this we only want 6 values here for our answer because we only had 6 runs. Doesn't matter about the taps, the flow rate is going to be the flow rate that we set it at for each of these 6 runs. So for that, that's why we have Q actual equals zeros of 6, 1. So we're just creating a vector here. So we have basically Q actual for run 1, for run 2, 3, 4, 5, and 6. Same thing for the theoretical flow rate. Same thing for the discharge coefficient here. That's Q actual divided by Q theoretical. Same for the Reynolds number, and same for the head loss. Okay, so we're almost ready to start doing the actual data processing. But before we do that, I'm going to initialize the axial position. So okay, I'm going to write another comment here. Say begin at 0, not at 2.8575 centimeters. Take that out. Okay. So if we type in X right now, let me clear this. I did a different run for a different program up here. So let's run our program here. Okay, if I type in X, we see that we're starting at 2.8575 centimeters. For the sake of our plots, I want to have this start at 0. So that's why we're going to start this axial position at 0 centimeters and not 2.8575. So for that, we'll just do X equals X minus X1. And we'll suppress that output. Now if I run this again, and now if I type in X, we see it's starting at 0 instead. Okay. Last thing before we start the data processing, we're going to set the throat diameter. Okay, so for that, I'm just going to type D4 equals D underscore T, and that's just going to, correspond to, in our experiment, station 4 was for the throat. So we had D throat up here, so I'm just assigning D4, or D of 4, to the throat. Okay, so what I've done here is I've just started this block of code. And what we're going to do now is solve for the theoretical and the actual flow rate for the system. So I've started out one line here for the volume. So like we said in class, the volume is just going to be the weight divided by the density of the water times the gravity. Okay, so now I'm going to start a for loop. And with that, we're going to solve for the actual flow rate and the theoretical flow rate. So we're doing for I equals 1 to 6 because we have 6 runs. So if I go back to our time spreadsheet right here, we have run 1, run 2, 3, 4, 5, and 6. And then the time for each time that we added a 15-pound weight. Okay. So now I'm going to put in A equals Polyfit. Okay, so we'll talk about this. So what I've done here is I'm using the Polyfit command. And what this is going to do is it's going to fit a linear curve through our data with this Polyfit command. So this is going to make it much easier for us to deal with the data that we collected in the lab. So our actual data, not the theoretical equations, basically. So for the Polyfit command, our first variable here, t, that's going to specify our x-axis. And then what I'm doing here is I want all of the rows for the time. And then this should be an I. Sorry, I confused myself for a second. So we want Polyfit. On the x-axis, we want the time. And then we're going to plot that against our volume. So we have a volume over time, essentially. And that's going to give us our volumetric flow rate. So this I right here, that's going to be, so we do that for every run. And then this 1 on the end, that just means we're going to have a linear curve and not something like a parabola or something like that. So again, I'm going to go over this briefly one more time. We have the Polyfit command. We have this number 1 here on the end. So that means we're going to fit a linear curve through our data. I have time, that's on the horizontal axis, and then I have volume on the vertical axis. So if we get the slope of that, we're going to do volume by time, and then we're going to get the volumetric flow rate. So to do that now, we have Q actual of I, so we want to iterate for all 6 runs, equals a sub 1. So what we're doing here is I'm going to set the slope of our curve equal to the flow rate. So let me just run this code and then I'll show you what I mean. Let's run that. I forgot to suppress that. Okay, so if I look at A up here, I have these 2 values. So basically, in value number 1, that's my slope. You know, y equals mx plus b. So we want the slope there for our flow rate. So that's what I'm saying right here. I'm saying set Q actual, so our actual flow rate for each run, that's I for runs 1 to 6. Set that equal to the slope that we have from this Polyfit command. And that's going to give us our flow rate. Alright, so let's go do the theoretical flow rate now. I'm just going to type this out and then I'll come back and we'll run that. Okay, so I've gone ahead and I've typed in the theoretical flow rate. And that's just this equation right here, number 14, where D2 is going to be the throat diameter. So I've typed that in, so you'll see in here I have 2 times the gravity, and in my code I have 0.02 times the gravity. That's just because for the head part of my code, H1 and H2, I have that in centimeters in my code here instead of meters, so I'm just adjusting for that right here. So if we run that and we look at our flow rates here, I have Q theoretical and Q actual, and we can see that they're pretty similar just by I for right now. Okay, so we've done that. Now we're going to do the theoretical and the actual pressure distribution. So we're going to keep this in terms of head. So what I'm going to do here is for I equals 1 to 6, and then for j equals 1 to 11. Okay, and I'll do the actual head. Okay, so here's what I've done. I've done for I equals 1 to 6. I'm doing that for all 6 runs that we've done. Then I'm doing another counter here for j equals 1 to 11. I'm doing that for all of the taps that we have. So we had 11 taps, so I want to get that head for each of those taps, and then for all of the runs, for I equals 1 to 6. So if I go to H here, this is what we imported earlier in the code. So if we go up here, we have all of this pressure head data that we've imported, and then we separated it into its own array, which we were just looking at right here. So as we have it set up, we have our columns for the 6 runs, and then all 11 of these rows, that's for all the pressure taps that we have. So I want to keep it kind of in that same format, so I'm calculating the actual pressure distribution here. So I'm doing each actual, I'm doing j comma I, so I want to keep it in that format where we have the taps on the rows, and then in the columns we have the runs. Okay, and then for this pressure distribution, we're doing that for each tap compared to the throat. So I'm doing h of j, so for whatever tap we have, and then I for the specific run. So if we imagine that we ran this code, we're going to start out by doing the pressure distribution for the first tap for the first run. And then we're going to subtract that for the 4th tap, that's the throat, for the first run. Okay, so that's the kind of idea. So if we run that, and I go to H actual, here we have it here, and we have our pressure distribution. So we see tap 4, that's always going to be 0, and that makes sense because we're just doing the throat minus the throat. Okay, I'm coming from the future right now. I thought I recorded this part, but I guess I didn't. So I already have all this code written out here, but what I've added on is the theoretical head right here, so in this line. So all that is this equation from your handout, but it's just this part. So just take a look at that. So we're doing 8 times our actual flow rate, but in this case theoretical, and then we're going to divide that by pi squared times g. And then also what's going to change is for our actual code, we're doing 1 divided by the diameter at the throat, and then minus the diameter for each tap, so that'll be j. So to reiterate, the only change that we're going to have here is 8 times the theoretical flow rate, and then 1 over the diameter of the throat, and minus 1 over the diameter for each tap, so that'll be for d sub j right here. Then we're going to multiply that by 100, so our units are in centimeters. So just make sure you write down the code like that. Then I also have this section here for the discharge coefficient and the Reynolds number. So for that, we're going to go from a counter of I equals 1 to 6 for the 6 runs. Then the discharge coefficient, that's just a simple code. We're doing the actual flow rate divided by the theoretical flow rate. And then we have the Reynolds number. We're going to do that for each run as well. And I just have this written in a different format than you might typically see the Reynolds number, but it's the same thing. So we're doing 4 times the density of water times the actual flow rate. And then we're going to divide that by pi times the viscosity of the water. And then also we're dividing that by the throat diameter. So just do this, and then we'll go back to where I left off the video, which is at this part right here for the head loss. So all I've done now is added this last block of code to find the head loss from the inlet to the outlet. So for that, all we're going to do is take the height of the piezometer at the inlet and subtract that from the height of the piezometer at the outlet. So I'm just doing for I equals 1 to 6 for all of the runs, and we have h of t of I is equal to the height at the first tap minus the height at the 11th tap, which is the outlet, and I'm going to do that for each of the runs, so we have I right there. So now we'll get started with the plots. So I'm going to start with the pressure distribution. So I'm going to start it out by doing figure and then 1. That way I can separate all my figures and have them all appear. Okay, so what I have here is plot, then x, that's going to be the axial position that we have on the horizontal axis, and then we have h actual. And then what I've done here is I'm only going to plot for the first run. So I have a colon, that's for all of the taps, and then comma 1, that's for the first run. Then here I have the marker for in blue, and then I'm going to have O's. Then I'm going to type hold on. Let me go back here. Okay, so now I'm going to plot the theoretical distribution for the same kind of thing here. So I'm going to plot it for all of the taps in the first run. I'm going to plot it in blue, but this time with dashes. So if I run that, we have our actual pressure distribution in the circles here, and we only have 11 points because we only had 11 taps. And the theoretical one, that's in the blue dashes. Okay, so you could do all of them on the same graph, but that's going to get really cluttered for the 6 runs, and really you're going to have 12 plots here because you're doing the actual and the theoretical distribution. So I'd recommend doing up to 3 per graph, so 3 runs per graph, that is. And then you could separate them, so like for run 2 I could do that in red, so red circles or red stars or whatever you want to do to make it nice and organized, but make it distinct, and then also put a legend in there. So I'll do that right now. Okay, if you run that, now we see the markers, that means the actual pressure distribution and run 1, and then the dashes is the theoretical pressure distribution and then run 1. Okay, so you can, title this whatever you think is best. I just, thought of the first thing that came to my head on the spot, so make it something that makes sense though and differentiates it from the actual pressure distribution to the theoretical. Okay. So what I've done now is I've just added some labels and a title. So make sure you include that in your graphs as well. Now if we look at this, we can see our axis. We could fix some things like make this go from 0 to like 26 or something like that. So if you want to do that, go in here, axis, then I'm going to go from 0 to 15 on the horizontal axis, and then 0 to 26. So if I run this again, now it's a little more compact, and we can move the legend down here so we can see the whole graph. Next thing, discharge coefficient. So we'll do plot, then I'm going to do the Reynolds number divided by 10,000, and you'll see why in a second, and then we'll do that against the discharge coefficient. So if I just plot this right now, this is what it looks like. It looks, I guess okay, but it's kind of weird. So we did the Reynolds number divided by 10,000, just so we have some nice numbers down here. If we took out 10,000, and we plotted that, then we have it like this, which is fine too, but I don't want this there, so we could just do Reynolds number divided by 10,000, and then we can have our x label to indicate that it should be times 10 to the 4th. Up to you though, you don't have to do that. So now I'm going to clean up our graph here, because again it looks kind of weird. I would rather have this, more linear. So what I'm going to do is change the axis just like we did up here. So I'm going to go from 0 to 4, and then on the vertical axis go from 0 up to 1.2. Now if I run this again, now it looks like this, so it looks a lot better in my opinion. You can do what you would like to do though. Okay, so now we just need to add the labels for this graph, and then you'd be good to go. Okay, so I've added the X label and the Y label here. I have it times 10 to the second, because I have this instead in centimeters cubed per second, and I forgot a parentheses there in the title, but you can add that on your own report. Make sure you do that. So what I should have done though for these graphs is not made them a continuous line, because that's not really the case. We were using the actual data that we had, so we had Q actual. So what we should have had was 6 data points here, not really this full continuous line. So what I'm going to do instead is make them again blue markers. So we'll just do that. We'll run that. And now instead we have these 6 points right here. And then I'll do the same for this plot. Okay, so we'll do that, we'll run that, and now it's like this. So at this point, you could leave it like this. This is what I told you, that you don't have to do the curve fits if you don't want to. So here we would use a 3rd degree polynomial, I think. And for the head loss, we would use a power function. So basically, if you did that, you would have a nice little curve fit going through here. But you don't have to do that again if you don't want to. That would make it look nicer though. But anyways, at this point, we are technically done with our graphs. Obviously, for my figure 1, I would need to have the 2 other runs on this graph, and I would make another graph where it runs 4 through 6. But this is the main gist of how to plot your graphs. I hope you make them look better than I have them in here. But that's pretty much it. I'll do one more thing though. When you're going to export your graph here, go to Export Setup. And I'm kind of trying to remember this on the fly. So we want to make sure that the actual graph looks good once you put it into your Word document or you put it in LaTeX. So what you're going to do is go to Export Setup and make sure your resolution is 300 or 600. Make it something that is nice and high. Then we'll go to Export and make sure you save it as like a JPEG or a PNG, or if you're really good, save it as a vector. If you save it as a vector, it's gonna look fantastic in your report. So make sure you just do one of those 3, and if you're saving it as a JPEG or a PNG, make sure this resolution is nice and high. Okay, so that's it. That's the workflow for this first lab.